Ladies and gentlemen, welcome back to lesson 13 in group theory. This lesson will talk about the commutator subgroup G prime. But what is the purpose of this lesson? Well, we love commutativity in groups. We love having the property that A times B is equal to B times A. This reduces a lot of calculations and it makes life easier for us when we want to study groups. But sometimes, even though the group is not an abelian group, that is, the property does not apply for all of the elements in the group, we want to see how close this group is to being an abelian group. Maybe it is really that close. Maybe it's not close at all. Well, if our group G is dirty, unfiltered water, being non-abelian, we hope to reach clean water by taking the commutator subgroup of G, which is called G prime. I will be explaining the exact process that happens during the lesson. But the process here essentially is to give us a more abelian group, more abelian, more commutative group. And we can repeat this process with G prime to get an even more commutative group, which we call G double prime. Repeating this process over and over, we might eventually yield an abelian group. Or we might never end up with that group. In any case, this gives us a measure of how close G is to being an abelian group. So after defining commutator and commutator subgroup and explaining this process, I will give you some examples of commutator subgroups in the symmetric group Sn. So let's get started. The first definition of our lesson concerns the commutator. Let G be a group and A and B two elements in G. The commutator of the pair AB is defined to be the brackets AB, which is equal to A times B times the inverse of A times the inverse of B, which of course is an element in G. Note that if we reverse the order in which we write our elements, of course, the definition will give us B times A times B inverse times A inverse. All what you're doing is following the definition given to us. If A and B commute, then we find that the commutator AB, defined to be A times B, A inverse times B inverse, is equal to B times A times, we can play around with this as well to say this is equal to BA inverse. This is by a property that we've seen in lesson 3. And because A and B are commutative, we can rewrite the order of BA to be AB inverse. And now we have that BA times B inverse times A inverse by the same property that we used here. And so this equals, by definition, to the commutator BA. In conclusion, if A and B commute, then the commutator AB is equal to the commutator BA. Now that we have defined the commutator, it is time to define the commutator subgroup. We've seen last lesson that we can generate subgroups from subsets. So when we take the commutator, we will take, in fact, the commutator of all of the elements in G, and that will be our subset on which we will generate our subgroup. So more formally speaking, let G be a group. The commutator subgroup of G, noted G, G, or G prime, which is also known as the derived subgroup, is given by G prime, the subgroup generated by all the commutators AB for all A and B in the group. So essentially, this is our subset in G, and we are generating based on that subset. So we are taking the products of all the elements in this subset and the inverses of these elements in this subset. Note that G prime is in fact a subgroup of G, and I'd like you to prove that formally. Prove that this G prime is a subgroup of G. If G is abelian, in other words, if all of the elements are commutative with each other, then G prime is just the subgroup containing the identity, what we call the trivial subgroup of G. And the reason is because if we take for any commutator AB, this will be equal to A times B times A inverse times B inverse. And because any two elements in an abelian group commute, we can commute the elements B and A inverse to give us A times A inverse times B inverse. But we know that A times A inverse is equal to the identity, and the same goes for B times B inverse. So this is just equal to the identity. So the entire subset of G here will just contain the identity, and the subgroup that is generated by the identity is nothing but the trivial subgroup that contains only the identity, since all products and all inverses of the identity is just that, the identity element. Now, as I've briefly mentioned in the introduction, the process of taking the commutator subgroup is not a process that we only have to do once. We can do it multiple times if needed. So we start with our G, and then we take our commutative subgroup, and then we can take the commutator subgroup of G prime to have G double prime, and then we can take the commutator subgroup of that as well, and we repeat the process a certain number of times. It could be an infinite number of times. So how do we differentiate between a finite number of times or an infinite number of times of taking the commutator subgroup? Well, we call G a solvable group if there exists a finite number n such that the n minus first iteration of taking the commutator subgroup of G is abelian, and we have the sequence that starts with G, and then G prime, and then G double prime, G triple prime, all the way to G n minus 2, G n minus 1, and because this is abelian, the commutator subgroup of Gn minus 1, which is Gn, is just the identity element. So G is solvable if at one certain point we will arrive at an abelian group, which is Gn minus 1, at which point if we take the commutator subgroup of that group, then we will get the identity. So we essentially win and get a solvable group if we arrive at the trivial subgroup of G. But if not, then G is not solvable. If we were to talk about our analogy with the water filtration, then a solvable group G is water that can be eventually filtered out a number of times until we receive 100% pure clean water. And an unsolvable group G is one where we will never get that 100% purity. Let us now look into a lemma that will be very useful for us throughout this lesson. Let G be a group and A be an abelian group. Let phi be a homomorphism that takes an element from G and gives you an element in A. Then the result says that the commutator subgroup G prime is a subgroup of the kernel of phi. Okay, let us prove this lemma now. To prove this lemma, note that G prime is generated by all the commutators AB of the group G. Since ker phi is a group, because a group is by definition closed under the products and the inverses, and this is generated, that means we're taking all the products and all the inverses of the commutators AB. It suffices to prove that the commutator AB is an element in ker phi for all A and B in G. Because once we prove that all the commutators lie in curve phi, that is, this set lies in curve phi, because curve phi is a group, we know that all the products of these commutators and all the inverses of these commutators also lie in curve phi, which means that essentially G prime also lies in curve phi. So to prove that the commutator AB lies in curve phi, we need to take phi of that commutator, and we hope that phi of that commutator gives the identity element in A. So phi of the commutator is equal to phi of A times B times A inverse times B inverse by definition of the commutator of AB, and this equals to phi of A times phi of B times phi of A inverse times phi of B inverse, because phi is a homomorphism, so we can do this splitting up of elements here. And now, since these elements are in A, we're not in G anymore, remember? The image is in A, and A, we've said, is an abelian group, so we can commute the images of phi A, phi B, phi A inverse, phi B inverse. In particular, we can switch around the places of phi B and phi A inverse to get us phi A times phi A inverse times phi B times phi B inverse to give us the identity in A times the identity in A, which of course is the identity in A. Thus, this element is in the kernel of phi. So, we have succeeded in proving that the entire subgroup, the entire commutator subgroup, lies in the kernel of phi. But we want to see that it is also a subgroup of the kernel of phi, but that is possible because we know that G prime is a subgroup of G. So if G prime is a subgroup of G and G prime is contained in curve phi, then absolutely we can say that G prime is a subgroup of curve phi. So if it's a subgroup of G, that means it's well behaved. So it does not matter if you take a smaller subset that contains G prime, which in this case is the kernel of phi. Therefore, terminating the proof of this lemma. Now that we have defined the commutator subgroup, it is time to put it to use in knowing what is the commutator subgroup of the symmetric group and of the alternating group Sn and An respectively. This proposition will give us exactly that. The first result says that the commutator subgroup of Sn is equal to An for all integers n. Number 2 says that the commutator subgroup of An is equal to the identity only for n equals to 1, equals to 2, and equals to 3. The third result says that the commutator subgroup of A4 is equal to V4, the 4 Klein group. We have encountered this group earlier, but I will refresh your memory about it. And the last result says that for n greater than 4, we have that the commutator subgroup of An is itself. Let's get started with the proof. The proof of the first part will be as follows. We will use double inclusion to prove the equality here. So prove that Sn prime is a subset of An and that An is a subset of Sn prime. So to prove the first inclusion, we're going to use the lemma that we've seen earlier in this lesson. So the lemma says that if we can somehow prove that An is the kernel of some homomorphism, then Sn prime, the commutator subgroup, will be a subgroup of the kernel, which is An. And that is exactly the case because an is the kernel of the homomorphism which is sine. The sine homomorphism, if you remember, was a homomorphism that took a permutation from Sn and gave you a number that is either 1 or -1. So because the sine is a homomorphism and an is the kernel, that means by the lemma, the commutator of Sn is a subgroup of the kernel of the sine homomorphism, which equals to an. So not only it is a subset of an, but also a subgroup of an. So we got even more than what we wanted. So that's the first inclusion. The proof of the reverse inclusion will be done according to cases of n. I will be dividing the cases, the first being if n is equal to 1 or n is equal to 2, and the second case will be when n is bigger than or equal to 3. So if n equals 1 or n is equal to 2, what is a n? Well, a n, if you remember, is the set of even permutations. If n is equal to 1, then we only have the identity. So an here is the identity, clearly, because we only have one element. So there is only one possible permutation for one element. And the identity is an even permutation. And the second thing is that if n is equal to 2, then we only have two elements. And the only thing we can do with these two elements is either the identity or we can perform a transposition of these two elements. However, a single transposition like that is not an even permutation because it has an odd number of transpositions, which is 1. So this is not an element in an. Therefore, an is also going to be equal to the set containing the identity for both n equal 1 and n equals 2. And of course, this subgroup containing the identity is included in Sn prime, because Sn prime is a subgroup after all. So we have that Sn prime is equal to an for n is equal to 1, n equal to 2. Very trivial and very clear. Now, for n is bigger than or equal to 3, what can we say about the commutator of an element in an? So let's take an element in an. An element in an, what is it made of? It's made of even number of transpositions, right? Because an is the set of even permutations. But an even number of transpositions is generated by pairs of transpositions. So it suffices to take a single pair and we see what is the commutator of that pair of transpositions. So let's take the pair of AB and AC. Okay? And this pair is equal to, by definition of the commutator, AB, AC, and the inverse of AB, which is also AB, the inverse of AC, which is also AC, and this equals to, after some computation, ABC. It equals to a 3-cycle. Interesting. So if you take the commutator of a transposition pair, we get a 3-cycle. So this applies for no matter what pair we use, whether they contain the same elements, an element in common or not, we get in the end a 3-cycle. So this is interesting. So we have for any A, B, and C, if we take a 3-cycle containing A, B, and C, we can make it equal to the commutator of a pair of transpositions. This means that, mathematically speaking, the set containing the 3 cycles is contained inside the commutator of Sn. So the benefit in proving that the set of 3 cycles is contained in the commutator of Sn is that if we take the subgroup generated by the 3 cycles, we can also say it is contained in Sn prime. And why is that? Well, that's because Sn prime is a subgroup. So that means it is closed with respect to products and with respect to inverses. So it is quite all right to take the subgroup generated by the 3 cycles and say that this subgroup in itself is contained in the commutator of Sn. But this subgroup is exactly proven and in last class, lesson 12, to be An. So we have just proved that An is contained in Sn prime, therefore proving both inclusions and in the end concluding that Sn prime is equal to An, completing the proof of the first part of the proposition. The second part of the proof is pretty straightforward. We want to prove that the commutator of An is just the trivial subgroup for n is equal to 1, 2, and 3. To do that, let us list what is An for 1, 2, and 3. We know already that An is just the trivial subgroup for n is equal to 1 and 2. And for n is equal to 3, we have 3 elements. So the only even permutations that we can have for 3 elements is the identity permutation and the 3 cycle. So A3 is equal to just the identity and the 3 cycle, since we know that An is generated by 3 cycles. So in both cases, we find that An is an abelian group. And because An is abelian, if we take the commutator subgroup of an abelian group, we get back the trivial subgroup containing just the identity, completing the proof of the second part of the proposition. The proof of the third part of the proposition will be done in a similar way to what we did earlier, where we proved it using the double inclusion. So the first inclusion is easier. V4 contained in A4 prime. Remember, V4 is the fork-line group containing 4 elements, the identity, and the 3 double transpositions, 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. So we would like that all of these elements could be written as the commutator of some product of 3 cycles, because we know that A4 is generated by 3 cycles. So we will write 1, 2, 3 and 1, 2, 4. The commutator of the product of these 3 cycles is equal to 1, 2, 3 times 1, 2, 4 times the inverse of 1, 2, 3 times the inverse of 1, 2, 4. And this equals, after some calculation, to 1, 2, 3, 4. So already we can write the first element in V4 as the commutator of some product of 3 cycles. So we can say that 1, 2, 3, 4 is included in A4 prime. The same can be done for the other elements, 1, 3, 2, 4, and 1, 4, 2, 3. And I'll leave that to you as a little exercise to give me what this equals to as a commutator of a product of 3 cycles. So we have that both these elements are also in A4 prime. And since A4 prime is a subgroup, we know that the product of this element with itself is also an element in A4 prime. But the product of this element with itself is the identity. So the identity is also an element in A4 prime. And therefore, the entire group V4 is proven to be contained in A4 prime, proving the first inclusion. All right, so the less obvious direction of inclusion is proving that the commutator subgroup of A4 is included in V4. What we'd like to do here is we'd like to use the lemma again. The lemma that said, if there is a homomorphism such that V4 is the kernel of that homomorphism, and the codomain of the homomorphism is an abelian group, then we can say that A4 prime is a subgroup of the kernel of that homomorphism, which equals V4, and then we're done. So the tricky part here is to find that homomorphism, to construct it. So we consider the homomorphism phi that goes from A4, it needs to go from the group A4 all the way to an abelian group. And the abelian group that I'll choose here is the cyclic group of 3 elements. If you don't remember what cyclic groups are, highly recommend you go back in the playlist and click on the lesson of cyclic groups. So the other condition that we need is that for the lemma to succeed, we need that V4 is equal to the kernel, so such that V4 is equal to the kernel of that homomorphism. In other words, if we take phi of any double transposition, any element in V4, that gives the identity. Okay? So we want that phi of any double transposition gives the identity, and phi of any other thing does not give the identity, because we want to phi V4 to be exactly equal to the kernel. So the elements of V4 are exactly the elements of the kernel. They're exactly the elements such that phi of these elements is equal to the identity. So we can't explicitly define our map, but we can logically assume what it is. We know that C3 is the cyclic group of 3 elements equaling the identity, G, and G square. But we know that G square is the inverse of G, since G times G square is equal to G cubed, which is the identity. So we can just replace G square by G inverse. Now that we have defined our phi, we need to complete its definition by explicitly stating where it sends each element of A4 to. We know that A4 is generated by 3 cycles. This is a result we've seen before. So we can work on just the generator and see where phi takes each generator to. And each generator is a 3 cycle. So phi of 3 cycle. That is the beauty of generators. To understand where phi sends all of the elements in A4, it only suffices to work with 3 cycles, because since phi is a homomorphism, phi of a product is equal to the product of phi. So it really behaves so nicely. Just because of that, we can work on just the generators, which are the 3 cycles. Here is the list of all of the 3 cycles of 4 elements. So we have these 3 cycles, and we would like to know where phi sends each 3 cycle to. Since we have in C3 only 3 elements, there are only 3 possibilities of where phi sends each 3 cycle, either the identity, or G, or G inverse. But the identity, we've said it's only for double transpositions. Double transpositions that contain disjoint transpositions, no elements in common. So none of these 3 cycles, they are made up of disjoint transpositions, so none of them are sent to the identity. They are either sent to G or G inverse. Now, without loss of any generality, I can assume phi of 1, 2, 3 to be equal to G. I could have chosen any of these 3 cycles and could have said that phi of that 3 cycle is equal to G. But because I chose it to be 1, 2, 3, I have to now be committed to that choice. So phi of the 3 cycle 1, 2, 3 is equal to G. So based on that choice, I want to know where phi sends each of the other 3 cycles to. I can no longer assume where phi sends the other 3 cycles to. I have to calculate what that equals to. Luckily, I have a very powerful technique that enables me to do that. So, the question here is whether phi sends the 3 cycle to G or G inverse. And the answer lies in this information here. Recall that if sigma is a permutation containing x1, x2 all the way to xn, then the conjugate of sigma by tau is equal to tau x1, tau x2 all the way to tau xn. And if we apply phi on that, we get back phi of this conjugate equals phi of tau times phi of sigma times phi of tau inverse. But because C3 is abelian, the group C3 is abelian, we can flip around and get back the identity here, which equals to phi of sigma. So notice that if we apply a conjugate on sigma, the result of the phi would be the same for phi sigma. So here, we will try to get 1, 2, 3 to get it equal to 1, 3, 4 by applying a conjugate on 1, 2, 3. And this is what we get. If we start with 1, 2, 3 as our sigma and 2, 3, 4 as our tau, this 4, 3, 2 is our tau inverse, we get back indeed 1, 3, 4. Simply, how did I do this? I used this formula here. Constructing tau was the most difficult part. I had to construct tau such that, because here, for example, 1 is sent to 1, so tau is going to fix 1, so 1 is not going to appear in tau. And 2 is sent to 3, so I need to make sure that tau sends 2 to 3. And lastly, 3 is sent to 4, so I need to make sure that tau sends 3 to 4. And tau inverse, of course, is just reversing all of the elements of tau. So I managed to find a 3-cycle tau such that this equation is valid. And if I apply phi of that, then I get back phi of 2, 3, 4 times phi of 1, 2, 3 times phi of 4, 3, 2. But I know 4, 3, 2 is 2, 3, 4 inverse. And I can use property of homomorphisms. And I know that the group is abelian, so I can switch these two around. And this will cancel with that then. And I get phi of 1, 2, 3, which is equal to G. So you can see that phi of 1, 3, 4 is equal to G at the end of the day. So that way I calculated phi of this 3-cycle to be equal to G. And I can do the same for these 3 cycles. Now the question you might ask me is, what about these 3 cycles? What happens if I apply phi on those? And the answer I'll tell you here is that the problem with these is that we cannot go from 1 to 3 to 3 to 1 easily using conjugation. If we try to do that, what we get is this bad boy over here. We get that tau is this permutation, and tau inverse is this permutation. But remember, what is the domain of our definition? The domain of our definition is A4, the set of even permutations. Is tau here an even permutation? No, tau here is not an even permutation because even permutations are ones that are generated by 3 cycles. This is not a 3 cycle, so I don't know what that's doing there. So this is not even valid as an element of A4. Here it worked because tau is a 3 cycle. It worked here. So we do not have such a conjugacy from A4. So these all cannot be equal to G. And therefore, the only other possibility is to be G inverse. So phi of these elements is equal to G inverse. And now we have completed our construction of phi. And phi indeed is a homomorphism. And we can say with confidence that we can use now the lemma that says that since V4 equals the kernel of phi and A4 prime is a subgroup of the kernel, we have that A4 prime is a subgroup of V4. So we even got more that we wanted. We wanted for it to be just a subset, but we got more. We got a subgroup of V4. And now we can say that the commutator subgroup of A4 is exactly equal to V4 by the double inclusion, completing the proof of the third part of the proposition. To prove the last part of the proposition, we want to say the equality of sets an prime is equal to an for all integers n bigger than 4. We will use again the double inclusion. The first inclusion is quite easy. We already know that the commutator subgroup is a subgroup of the original group. So this is already done. Now we want to prove that an is contained inside the commutator an prime. We know that an is generated by 3 cycles. So we want to just show that a 3 cycle can be written as the commutator of a product of some 3 cycles. And this is exactly what we'll do. The commutator of 1, 2, 4 and 1, 3, 5. Note that we can have 5 elements here because n is bigger than 4 strictly. This is equal to 1, 2, 4, 1, 3, 5, the inverse of 1, 2, 4, the inverse of 1, 3, 5. And this, after some calculation, yields us 1, 2, 3. So for any 3 cycle, we can get this is equal to the commutator of some product of 3 cycles, meaning that the 3 cycles are in the subgroup, the commutator subgroup. But since it is subgroup, it is closed under the group operation and inverses, so the whole generation of the 3 cycles is also inside an prime, which is an. So this gives us that an is contained inside an prime. And now we have the inclusion in both sides. We can conclude that an prime is equal to an for all integers n bigger than 4. This completes the proof of the entire proposition. The previous proposition was important in telling us what is the subgroup commutator of Sn and an for all n. Now a corollary is a direct result that comes immediately after the proposition. This corollary says that Sn is a solvable group if and only if n is less than or equal to 4. And to prove this, we will immediately use the proposition we've just proved. If n is a number between 1 and 3, we see that Sn, if we take the commutator subgroup of Sn, since n is between 1 and 3, by the proposition, this is equal to an. And if we take the commutator subgroup of an, we get the trivial subgroup. And we have said that a group is solvable if after a finite sequence of iterations of taking the commutator subgroup, we eventually reach the trivial subgroup. So Here, Sn is solvable for n between 1 and 3. If n is equal to 4, and we take, of course, the commutator subgroup of Sn, we get back the subgroup A4, and the commutator subgroup of A4 is proven to be V4, the fork-line group. But because V4 is an abelian group, the commutator subgroup of V4 is the trivial subgroup. So since we've reached the trivial subgroup after a finite number of steps, we have that S4 is solvable. If n is strictly bigger than 4, we want to show that it is not solvable, and that is simply the case because if we start with Sn, we take the commutator subgroup, we get An, and because the last proposition told us that the commutator subgroup of An is just An, that is just equal to An, essentially what we're doing is we're just getting back An, no matter how many times we we get the commutator subgroup. So there exists no finite sequence of taking the commutator subgroup such that we arrive at the identity. We're never going to get it back, the identity. We're just going to get back An. So in this case, Sn is not solvable. Group completing the proof of this proposition. Now the question that you might have in mind once you've seen the definition of a solvable group is, why do we call the group solvable? Why that name precisely? Well, the answer to that is very, very nice. The group is solvable if its corresponding polynomial is solvable. And what is a solvable polynomial? Well, what about degree 2 polynomials, ax squared plus bx plus c? We want to know what is the roots of this polynomial, and to do that we have the quadratic formula. We have obtained this formula using nothing but elementary operations: plus, minus, multiplication, division, squaring, and taking the square root. So if you can come up with this formula using these elementary operations, squaring, cubing, taking the fourth power, taking the nth power, or taking the nth square root, then this polynomial is solvable. So degree 2 polynomials is solvable. Degree 3 and degree 4 also have their own formulas. The formulas are a bit long, so I will not be writing them here, but they were found. Now, what about degree 5 and above? For many years, mathematicians have tried to find the formulas for those, but they could not. The reason for that is because there is none. It is impossible to find such a formula, and that has been proven using group theory. It has been proven that there is an interesting connection between solvable groups and polynomials. How is that? Well, if we have the polynomial, and the polynomial has its roots, let's say the roots are x1 and x2, then these form a set of roots. And this set, named E, we could perform permutations on this set. In this case, we could perform the permutation that does nothing. x1 is sent to x1, x2 is sent to x2. So this is the identity permutation. So exactly the way we took in symmetric groups. This is exactly S2, containing the identity permutation and the permutation that sends x1 to x2 and x2 to x1. So we find that we can get the group of permutations of the roots of the polynomial. And Galois theory is an extension of the study of group theory, where we discover that there is an interesting connection between the roots of the polynomials and the groups of permutations of these polynomials. And the result is the polynomials are solvable if and only if the groups of permutations of these polynomials are solvable as well. Solvable in the sense that we took here, that if we take a chain of taking the commutator subgroup, we will eventually end up with the trivial subgroup. So, because for n bigger than or equal to 5, we can never reach the we can never reach the trivial subgroup, we can conclude that polynomials of that degree are not solvable. And this is one of the most fascinating results that have arisen from Galois theory. And with that, we have finished today's lesson. If you've enjoyed, please leave a like and subscribe and share with anyone who would be interested in this fascinating topic. I'll see you next time with more and more results on group theory. Have a nice day and bye.